We have installed state-of-art equipment in the laboratory of tribology, and this tribology laboratory is also among 5 laboratories in India. This laboratory has already done MOUs with some advanced universities of the world, including Texas University and with other universities. We have got international and national collaboration in the field of materials. Tribological tests which we are conducting in our laboratory are unique in India, and this is the only laboratory in India which has low temperature as well as high temperature facilities. We have got the FIS scheme which we implemented, and we have already done research projects at international level with most advanced universities in the field of materials.
My name is Dr. Sheikh Shahid Salim. I am an associate professor in the Department of Mechanical Engineering. I joined this institution in 1993 and completed my masters from IIT Roorkee in machine design in 2002. I completed my PhD in the field of tribology in 2018 under the supervision of Professor M. F. Wani. My research interests include high temperature wear testing, friction materials, and biomaterials. I have completed and supervised 22 MTech theses in the field of tribology. At the institutional level, I currently am the chairman of the Central Research Facility Center, which houses some of the most sophisticated equipment like XRD, FE7, sputter coating.
I am Professor M. F. Wani, Professor Mechanical Engineering Department and in charge of High Temperature Tribology Laboratory. I have been working in this department for last 35 years. I have established one of the best laboratories in tribology in India, and we have developed the laboratory wherein we are able to develop the materials of our own, metallic materials and coatings, and then we test these materials in our laboratory. We conduct all tribological tests in our laboratory, and this laboratory is also known in the scientific world as High Temperature Tribology Laboratory. We have produced 13 PhDs in this laboratory and more than 100 MTech theses in this tribology laboratory. I am Professor M. F. Wani, Professor Mechanical Engineering Department and in charge of High Temperature Tribology Laboratory. I have been working in this department for last 35 years. I have established one of the best laboratories in tribology in India, and we have developed the laboratory wherein we are able to develop the materials of our own, metallic materials and coatings, and then we test these materials in our laboratory. We conduct all tribological tests in our laboratory, and this laboratory is also known in the scientific world as High Temperature Tribology Laboratory. We have produced 13 PhDs in this laboratory and more than 100 MTech theses in this tribology laboratory.
शीना डो खुद गर्दन को दर्द हो गया। हाँ फिर मत चलो मोबाइल मत चलाओ फिर मोबाइल में चलाओ क्या Koşana. Mesela Gautam acaba क्या है आखिर के साल सुन ये लोग अच्छी है Yanlışlıkla tamam doğrusu şu farkı. अच्छा मुझसे कल का भी क्या अगली का
सर वो ले नहीं रहा वो बोल रहा है कि यू कैन नॉट मॉडिफाई शेड्यूल एज द डेट हैज ऑलरेडी पास्ड
चल छोड़ चल छोड़ चल ठीक है सबमिट नहीं होता बोलेगा हमको मिस हो गया
सर अपने पास
हाँ मैं चेक से अब आप क्या करेंगे
ठीक है सर आगे
क्या करेंगे कितना आ गया ज्वाइन
सर आपका माइक चल रहा है
माइक क्यों में अच्छा समझ में आ चीज आगे हाँ जी हाँ गुड इवनिंग सर सर प्लीज चेक योर ऑडियो योर ऑडियो इज म्यूटेड सर इट इज म्यूटेड
Okay.
now it is okay maybe from NIT Bhopal. In fact, he was doing when I was in IIT Roorkee, he was doing PhD under Professor JSNE, Professor JL Bagoria.
Okay, okay, okay.
He's giving us some talk on solar energy, recent advances in solar energy. So all my known people with whom I have been.
No, I was initially thinking that probably I am the only one who doesn't have any connection with IITK, but there are other people also.
Okay, welcome to day 2 of the FDP. The title of the FDP is Thermal Characterization and Advanced Measurement Techniques. So today we have session 2, and our expert for the session is Professor Manish Mishra. So Professor Manish Mishra has done his PhD from IIT Kharagpur. Professor Mishra is presently working as professor in Mechanical and Industrial Engineering Department at IIT Roorkee. So prior to joining IIT Roorkee as professor, Professor Mishra has worked for more than 10 years as associate professor and assistant professor in NIT Raipur. So Professor Mishra, his research interests are in the field of heat exchangers, solar thermal systems, desiccant cooling, application of soft computing tools, and battery thermal management. Already, Professor Mishra has supervised more 11 PhDs and around 25 MTechs. Professor Mishra is having more than 50 publications in international journals of repute. Today, Professor Mishra will be delivering expert lecture in challenges in heat exchanger operation and measurement. So this session, the timing of the session is like this thing. So if Professor Mishra wishes, so he can divide the session 2 into 2 parts. So first session will be of 50 minutes, then he can, Professor can take a break of 10 minutes, then he can rejoin at 8, and from 8 to 8:50. Then after 8:50, we can have interaction with the students. So over to Professor Mishra,
Okay.
so that we can get
Okay.
enlightened by his.
Thank you, Professor Anand, for your kind introduction and nice words for me. So I'm sharing the content. Let's see if you
Okay.
can see that thing. Is it visible?
No, it's not coming up, sir.
It's not.
You have to just present now. You have to press the button present now.
For sharing, it is not giving me the option to share. That button is not working.
Present
Let me
now.
do it again. Let me do it again.
Sir, you can do it now. Yes, it has started now, sir. You have started presenting. Yeah, it's coming.
It has come?
Yes, it has come now. Now you can start your presentation, sir. So your screen is now visible to us.
Is it fine in the full screen mode?
It's full screen board. Now you have to show the presentation, sir.
Okay. So good evening, everyone. And
But sir, your presentation is not coming. Only your screen is coming. Nah. It's
is it?
showing Zimbra inbox, but you have to open your presentation also then.
No, it's open only. It's open.
But I can't see it.
It's open.
Huh? Sir, you can you reload the browser?
I am again stop sharing. Probably you may be seeing this thing. Stop sharing thing. Is it visible?
No, no, it's not
No?
visible. Now I can see you only. You have to just press the button, start presenting. So
No, but before that, I need to start either window or a screen or something.
uh, present now. You have to write that entire screen, or we have four buttons. Mic. This is come. Now your screen is visible, sir. So
Is it?
now it's visible. Yes, we can see it. Sir, please can you just click this button, hide, because it's coming. Hide. Just now it's wonderful. Sir,
That's
you can
fine.
go ahead.
Okay. So, good evening, everyone, and sorry for the initial glitch at this moment regarding this sharing. I hope we'll be having, if not very wonderful, definitely some satisfactory content I'll be providing. And at any time, if you need to interact regarding some content in between, uh, you are most welcome also. Otherwise, definitely we'll be having that discussion session at the end. Okay. So the topic, as what is mentioned here, is the challenges in heat exchanger operation and measurements. Uh, as far as the heat exchanger is concerned, I hope that at least the definition, background, the areas of application, and other things, almost everyone is knowing. But then when we go to deeper inside that design, manufacturing, operation of those heat exchangers, we find so many other things also which we probably have not come across while the regular study until we specifically go to the research aspects or the other things related to that. So apart from the basic understanding, which where from I'll start with, I'll slowly go to those aspects. Initially, in the requirement, where from we are selecting or designing the heat exchangers, and then what are the kind of problems we generally face during its operations, its manufacturing, and its testing. So when it is operation and testing, definitely measurement aspects automatically are built in. So definitely, I do not have any distinct, you can say, divider that this is for pure design and then operation and then testing. But definitely, I'll try to make it in that way so that you can understand that each of the aspects we are covering. Second thing, uh, some of the content definitely will be overlapping. So I hope you can understand because I cannot uh, extract one session exclusively compared to the other one. As far as the coverage is concerned, we'll start with the basics, the introduction. Then why at all we require heat exchanger requirements, we know. But when we go to different classifications, why at all we need those specific kind of heat exchangers, that's what we'll see. And what kind of requirements are there while designing those things? What kind of issues are come into picture? And what kind of basic problems we come across while facing any heat exchanger problem? Okay, so that also we'll see. During this thing, I'll just give you a brief that when we are solving any heat exchanger problem, whether it is BTech level or whatever, basically we are having two varieties of the problems. One is design problem, which we also call it as sizing problem. And second one is rating problem. Rating means nothing but the performance calculation, performance estimation one. So rating can also be considered as the problem of simulation ones, which nowadays so many people are involved with. And the designs are nothing but the calculation of the geometry, the diameter, length, all these things. When we are going for design, it's not simply any preliminary design and sizing values, dimensions we provide. A perfect designer is one who can optimize the design for the required conditions, objective functions, and so on. So definitely we'll touch a bit regarding the design optimization things. The challenges again faced during that process. Then we'll see how the performance estimation can be done uh, analytically, numerically, and then finally the physical testing, the experimental testing of the systems. Uh, while experimental testing, again, I'll give you some ideas, probably which may not be clear in general while we are focusing on our textbook reading, that how we define the testing in the practical field. So when we define heat exchanger is nothing but any equipment you can say which exchanges energy or the heat between fluids. Okay, like the energy interaction may also be there between one solid and the fluid also, but that may not be considered as. In extreme situation, of course, there is one particular case, the regenerative case, rather, regenerative heat exchangers, where in succession, the energy is transferred from fluid to a solid, and then in secondary process stage, the same energy, same heat is being transferred from that solid to the fluid. Okay. Then it is very common in very various applications. Chemical process industries, then cryogenics, aerospace, HVAC systems, automobiles, radiators, even nowadays, whatever those new electric vehicles are coming, we have got the battery, but within battery also we need to do the thermal management system, battery thermal management system, BTMS we call it as. So for that BTMS also we need to have some provision of the heat exchange system so that effective cooling of the battery is done. Then it may be also used in cooling of different established electronic equipments like the laptops, computers, all these things. And some of the cases we are using the same thing in artificial organs also. Further, as far as the bigger industrial applications are concerned, and the other, you can say, high-end applications in that sense. So it is the gas turbine blade cooling, where the different varieties of the cooling provisions are there, and all are one or the other varieties of the heat exchange provision only. When we are classifying the heat exchangers, we generally think of two fluids, and then in between there is one wall, rather one metallic separating sheet. So the energy exchange takes place. One side, one fluid is there, another side, colder fluid is there. But what is happening when the energy transfer takes place? This energy transfer basically takes place by different means. And by means of the energy transfer, the process of energy transfer by number of fluids, by the process by which the energy is transferring, by the surface area, the sizing, all these things, and the construction. We are having different varieties of the heat exchangers. Some of them probably you might have heard, you might have seen also in and around you. But at the same time, various heat exchangers are available which we may not be even knowing that these are heat exchangers. So how we are classifying, that's what we'll see now. So the definition wherefrom I had started, we are having one solid wall, and other two sides of that solid wall, we are having two different fluids, a different energy level or temperature level. So if I consider this concept, then basically it is the indirect contact type heat exchangers. And further, if I am going to direct contact, like we are having the cooling towers and those categories of the systems where the two fluids get mixed with each other. So either it may be evaporation or mixing energy and those concepts, the energy interaction takes place and ultimately we take advantage of the transfer of energy. So if it is this variety, then it is direct contact type of heat exchanger. Okay. Now, next is based on fluid. Uh, Normally, we know that there are two fluids in between. There is some wall or maybe mixed category type, as what I have just told, that cooling tower variety. But then there are so many varieties are the types of heat exchangers where the number of fluids are more than two also. So accordingly, we have got three fluid heat exchangers, four fluid, five fluid, and multi fluid. So there are multi fluid and multi stream heat exchangers also. Okay. Then next comes is the compactness or the surface area. When we are talking about the surface area, uh, we divide the heat exchanger basically into broad categories. One is the compact one. Compact means size is small, and non-compact means size is bigger. But what happens when I am defining the compactness? Basically, that compactness is decided by the surface area, the heat transfer area per unit volume. So that surface area per unit volume, if it is this 700 meter square per meter cube and above, this is a compact heat exchanger. While less than that is non-compact, means ordinary heat exchanger, whatever we are having, those are non-compact one, those tubular, shell and tube, whatever. Those are non-compact one where the surface area density, this beta is surface area density, that is less than 700 meter square per meter cube. Now, this again leads to another classification that this is applicable when the heat exchanger is having one fluid as gas, another as liquid. Okay. So if this is the case, this definition is fine. Otherwise, if it has got both sides, some or the other liquid, then that definition of surface area density changes. It becomes 400 meter square per meter cube. So if it is greater than 400 meter square per meter cube, it becomes compact. Otherwise, it is non-compact. So what is happening when the fluid, one of the fluid even is a gaseous one, the area of heat transfer is increased to 700 from this 400 value, then only we are defining it as compact one. Otherwise, it is a non-compact one. Okay. So this is one basic difference we are having, which generally we have not seen. Then next come is the construction, the geometry. We had seen the tubular variety. Within tubular, we know pipe in pipe, the concentric double pipe heat exchangers. Then we know the shell and tube heat exchanger. Then we are having coil type of the versions, the pipe coil, spiral tube, and so on. There are plate varieties also. Plate varieties means if you happen to visit the milk chilling plants, you might have seen the plate heat exchangers. Those plate heat exchangers are the PHE, what I'm writing here. Those are welded, gasketed, those varieties, means how the manufacturing has been done. Then within that, there are other varieties. One more variety is printed circuit board kind of thing. We'll see what that printed circuit board is. PCB heat exchanger, which is called it as. Then another construction variety is the extended surface by putting the fin over the tube or the plate surface. So instead of the plain tube, the bare tube, if we put the fin structure over that, whether that fin is a disc fin, longitudinal fin, whatever, accordingly we can categorize as the finned heat exchanger, whether that fin is over the tube or over the plate. Okay. And finally, it is the regenerative heat exchanger. Regenerative, of course, comes based on the type of the heat transfer, the mode of heat transfer, or otherwise in construction also I am considering this thing because it works on the principle of regeneration. So what happens, one fluid enters, it moves over one solid surface. That solid surface is generally a matrix surface or a porous media. So it acts as thermal storage. So fluid will be passing through that thing for a certain time being. Then that fluid will be stopped to flow. Next, another fluid will start flowing through the same porous media bed, and then it will extract that amount of energy. So that is regenerative concept of the thing. Within that, based on the construction, its operation, we are having further sub categories, whether it is fixed matrix type, rotary matrix type, and so many other things. We'll see that thing. Then based on the flow varieties, we are having single pass, multi pass. Probably you might have uh, gone those particular things while discussing the shell and tube variety, where we are putting the baffles. When we are putting the baffles, are putting the multi-pass of the tube. So we are putting one single tube element, and then same fluid is entering from the other side of the shell, again flowing through the same length. So it becomes two pass. So same thing may be there for three pass, four pass, and so many things. If we are further adding another shell in series, that is two pass of the shell also. So there may be multi-pass of the shell side, multi-pass of the tube side. Then based on so many other heat transfer mechanism, single phase, multi-phase, two-phase, we are having other varieties. What basically differentiates the heat exchanger? So if you had calculated something, means you had solved certain problem, one thing which comes into picture while solving any heat exchanger problem or even convection problem, which you remember as Reynolds number. How do you define Reynolds number? So Reynolds number is rho Vd by mu, but in heat exchanger calculations, we generally avoid this rho V and those things. So there is another terminology which comes into picture, that is Gd by mu, where G is mass flux velocity. Okay, and that D is now the hydraulic diameter, which also is called as equivalent diameter sometime. How we calculate that thing? You might have done this thing. It is 4A by P, where A is the free flow area and P is wetted perimeter. Of course, the calculation is not that simple. We'll see some specific example afterwards how to calculate hydraulic diameter for certain cases where the things are not usual, like tubular heat exchanger. Okay, so when it is hydraulic diameter, which decides the size of the tubing or the flow passage. What happens when I'm changing the hydraulic diameter? Basically, the total heat exchanger geometry, its function, behavior, everything is changing. So this hydraulic diameter dH, which I write as, this is basically the key factor in heat exchanger design and its practice application ever. Now you can see this is the basic the scale I have shown, hydraulic diameter. Uh, it is ranging from the 60 here to the other side. It is 0.15 or zero 0.1. Okay, so it is of course logarithmic scale. It is decreasing when I am moving towards right. Bottom side is another scale which says the heat transfer area density, the beta, which we had discussed just now. Based on that, we were defining whether the heat exchanger is compact or not. So when I am decreasing the hydraulic diameter, this surface area density is increasing. So corresponding to this 60, it is roughly 60 meter square per meter cube. This is the case of plain tubular uh, heat exchanger, tube in tube heat exchanger. Then I can have a multi-tube like shell and tube version. I can have the compact version. Uh, the thing is, radiators are the evaporators and condensers of the refrigerators, air conditioners, and so on. Then we are having gas turbine rotary regenerators, cryogenic heat exchangers. I'm moving towards right. The passages are becoming smaller and smaller. And the surface area density is increasing. And for the smallest passage, whatever I had seen, of the order of 0.15 meter mm, this is mm, of course, or 0.1 mm, correspondingly, the heat transfer surface area density is this 3 into 10 to the power 4, 30,000 meter square per meter cube. So enormously, this is increasing. At the same time, what happens? I am dividing, there is one divider. Here I am saying that from this side onwards, the flow becomes laminar. Now, you say how the flow becomes laminar. Laminar, definition of laminar is in general for a solid conduit, the tube flow. The definition of laminar and turbulent transition is up to 2300 we consider the flow to be laminar, and then from 2300 to 4000 it is a transition phase, and then 4000 onwards it is again a turbulent flow. But what happens when I'm decreasing the hydraulic diameter? One peculiar thing that changes means even when the Reynolds number is 1500, that turbulence starts. And sometimes when the hydraulic diameter is so small here, the laminar to turbulence transition may start even at the Reynolds number of the order of 1000 or less even. So that is what is happening. So whatever the fundamental philosophies we are having regarding the calculation of Nusselt number, Reynolds number, all these things, and ultimately the heat transfer coefficients through those fundamentals, that ultimately gets changed because now the Reynolds number at 1000 only the turbulence has started. So I need to see the turbulence philosophy accordingly. The calculation, rest of the calculations will be changed. Okay. Second thing, when I'm going towards right, that heat transfer surface area density is increasing and the hydraulic diameter is decreasing, you can see the kind of applications. For the smallest hydraulic diameter, the human lungs. This is the kind of application I'm having. Okay. And these are some of the industrial, and this of course is the human body I'm seeing. But if I see the other applications, here at the bottom, you can see the common boilers, condensers. These are at the higher value of the hydraulic diameter, 25 mm or so. Then when it is the refrigerator, air conditioners, evaporators and condensers, it is of the order of 2.5 mm or so, which is now within this compact heat exchanger category. Electronics cooling, those laptop, all those devices, it is of the order of 250 micrometer. It is further towards this and this side. Then these are some of the human body things where the hydraulic diameter is still smaller. Okay. And accordingly, then instead of dividing the heat exchanger in simply two basic categories as the compact and non-compact one, we are further dividing as the conventional channels, mini channel, micro channel, and so on, even nano channels nowadays. Okay. And now you can see just this is the value of hydraulic diameter, how the hydraulic diameter is changing accordingly. You might have seen so many applications of micro channels, mini channels, and so on. But how that micro channel is there, that is basically based on the hydraulic diameter. So once we calculate the hydraulic diameter, we define what category of the channel is. But apart from the definition of the channels, basically we are totally changing the flow behavior inside, and that ultimately gets reflected in heat transfer and the pressure drop phenomena, flow friction phenomena. Now, let us start with the simplest case. How basically we are having the two fluids and how we are assigning the two fluids on the two sides. So you are having two fluids, one definitely is hot, another is cold one. How to assign the two fluids? So where I should put the hot fluid, where I should put the cold fluid? That is the commonest question one can have. Means the person who is on the field. Otherwise, we can put it randomly. But what happens when we need to design the heat exchanger? Nothing is mentioned about. One thing we need to see that whatever is the fluid of interest, the decision is taken based on that only. Say, for example, I am having, say, tube in tube heat exchanger like this. Now, I am having one hot fluid which is flowing maybe outside or inside the thing. Now, if hot fluid is the fluid of interest for me, if I am keeping it outside in the annulus, what happens apart from exchanging heat with the inner fluid, that is cold fluid, it will also be exchanging heat with the environment. In spite of the fact that whatever provision regarding the insulation or the other check you'll be having, definitely it will be losing something. So if that is the fluid of our interest, what I can do, I can put that fluid inside the tube so that at the most, whatever maximum energy interaction it will be having, it will give its heat to the cold fluid outside, which is flowing through the cannulus. And then finally, that cold fluid, if at all it is interacting with the environment, because the energy level of cold fluid is smaller, so the chances of losing the percentage loss will be less compared to the case when the hot fluid is outside. Okay. Similarly, when I have got the option, one fluid is either steam or the gas. So, how to decide? Basically, it is based on the density. Uh, Steam or any gaseous fluid, which will be having low density, are the high specific volume. So it needs larger volume for the same mass flow rate. So if I'm providing the tubular passage for that, generally we may not be able to accommodate until the length of the heat exchanger is too large. Okay. So to avoid that thing, generally, whenever I am having steam or the gaseous fluid, the fluid is passed through the shell side. Generally, it is shell and tube heat exchangers. And that's the reason the condenser in the thermal power plant, whatever we select, that is generally a shell and tube heat exchanger. Okay. Now, suppose I have got any dirty fluid stream, which is maybe coming from some or the other part of the chemical process industry. So if that is the case, uh, I should put it on the tube side. Why tube side? Because cleaning is always a problem. Apart from fouling, if the contaminants are there in the fluid, definitely it will get deposited and affecting the heat transfer. Not only that, there may be clogging or choking up after some time. So just to avoid that thing, if it is in the tube side, tube cleaning is always easier. Definitely, you need to clean periodically, but it is always easier compared to shell side cleaning. Okay. Then, if it is high pressure steam or high pressure fluid, if I am keeping it high pressure fluid on the annulus side or the shell side, if it is shell and tube heat exchanger, then what happens? That high pressure steam, to accommodate that high pressure corresponding hoop stress, longitudinal stress, those things, the shell structure will be thick and the shell is definitely bigger. So it needs heavy material, the thickness, amount of material requirement will be more. So overall, it will be an expensive affair. Rather than that, if I put the high pressure fluid in the tube, so tube thickness definitely I can control very easily. And the total cost of the heat exchanger will still be lesser compared to what we were discussing previously. Okay. Further, we can also have the viscous material. We can also have some specific fluid where the fluid may be, you can say, reactant to the particular fluid, particular, you can say, solid material. So accordingly, then we can decide which side that particular fluid has to be sent through. Okay. Then based on the heat transfer coefficient, so many times what happens, you might have come across that the question comes, you might have faced this during your examinations, certain competitive examinations, and so on, that where actually the fins have to be provided. So fins are generally provided on the lower heat transfer coefficient side, H, where H is smaller. And where H is smaller, where the fluid is generally either gaseous fluid or comparatively it is much lower compared to the other side fluid heat transfer coefficient. If at all you are having heat transfer coefficient of the similar order, say one side it is 50, another side it may be 55 or 48 or something like that, you can put or install the fins on any side you like. We'll see how the construction of those fin versions are. But you can install the fins on any side. But if at all you have got gaseous fluid, generally we put the gaseous fluids as what we had seen, that it should be outside the tube rather in the shell side. So fins are also on the shell side. So this is how we try to correlate the fundamentals and select or design our heat exchangers. But definitely, when any of such thing is not there, you always have got the option to select whatever you want, seeing all those plus and minus points. Tubular heat exchanger, everyone probably are knowing. That is the starting point for the heat exchanger. That's what I'm just touching this thing and very brief. It may be parallel counter type, but then what happens when we go for higher area, definitely how long you can manufacture the heat exchanger. So length is basically the limitation, which depends upon the length of the shop floor you are having, the laboratory space you are having. So if at all you require more length than what you had already decided, then instead of elongating further in the lengthwise direction, we make a U-turn. So similar parallel lengths will be provided with a connection like this, a bend connection. And this is what is termed as U-tube or hairpin type of the heat exchanger. And now it's a pictorial view. You can see how many. Pardon? Hello. Yes.
Sir, please go ahead. Somebody had unmuted his this thing.
Okay. Thank you. So this is the practical, you can say, schematic photograph of the thing. Now you can see these are all tubular version of the heat exchanger, but in series there are so many hairpins. Okay. This is shell and tube. We know because this is the next version. Why at all we are going for the shell and tube? Because whatever maximum area of heat transfer we wanted to accommodate, we may not be able to provide it through even number of U pins or hairpin types. So instead of say 50, 100 number of hairpins, we thought of having a better design, and this is what is the better design. It may be a single shell and with multiple number of tubes. Okay, so this is shell and tube, and probably this design also is very common, and you know how to calculate for the basic parameters for this case. The advantage is it is one of the you can say most widely being used variety because of simple construction. The technology, because it is being used since so long, technology is so much matured, advanced, that people know each and every detail of the working, its manufacturing. So many alternatives are there, and the advantage of coping up with so many odd situations like too cold temperature, high temperatures, pressures, all these things. So all these extreme situations can also be handled. Why shell and tube? As what I discussed, we are so much of greedy people, so we want more heat transfer, so we wanted a better design. That's what. So I'm not going to do much of this thing. But apart from this, it has got so many other advantages. It has got varieties of the operating parameters, conditions, you can say, in terms of pressure or temperature. Maybe a temperature from you can say sub-zero to as high as 600, 700 degrees Celsius, because that's the metallurgical limit we'll be facing. And then pressure also is from very small pressure to very high pressure. Fluids of any type and size. This size, I'm telling this is the size in terms of the heat transfer area. 10 meter square, 2000 meter square. But definitely, when it is only the heat transfer area, probably we may not be able to imagine. So it is basically the surface area density. And if it is the surface area density, then if we go back, it is basically of the order of, say, uh, 60, 100, and those things, meter square per meter cube. Okay. Up to 100, you can say the shell and tube heat exchanger construction area density comes with. So there are basically tube bundles, and the tube bundles are fabricated, attached with a common, you can say, end are through the baffles like this. And then the whole bundle is inserted from the end of the shell, and then we fix it. And in between, there are baffles. How the construction of baffles? Again, there are so many varieties. And based on this, we are having the fluid flowing on the shell side. At the same time, parallelly, we are having fluid entering for the tubes. So this is basically two-pass uh, fluid entering for the tube like this, going here, turning back, second pass of the tube, and it comes out here. And this is the shell variety. It is moving like this. This is the shell passage. The main purpose in any heat exchanger, why at all I am uh, describing this thing, in spite of the fact that it is very common thing and you know most of the details of this, because when I want more surface heat transfer area, it is fine, but simply providing the higher heat transfer area may not serve the purpose sometimes. If flow rate is too high, what happens? It will enter and come out without without any significant time inside the exchanger. So if that be the case, the time inside the heat exchanger, if it is small, then probably the effective heat transfer may not be possible. So one additional parameter which comes into picture now is that there is residence time. Residence time means time inside the exchanger for the fluid. If we can increase that thing for the same heat transfer area, same surface area density, the effective heat transfer will be more and the effectiveness of the exchanger will also increases. So this is another provision or target or the objective will always be having for the same exchanger, and that is the reason that we provide number of baffles here. Okay, the type of baffle, there are various types of the baffles. Apart from increasing the residence time, it also creates turbulence. Say, for example, the fluid is entering here, it is going like this, it is going like this, it is further going like this. So instead of entering from the top and going other bottom, means traveling only this much of the width, it is now traveling 4 or 5 times of that width. So total residence time increases by 5 times. So that increases the chances of heat transfer. Definitely, the heat transfer increases and the effectiveness of the heat exchanger increases. Okay, so not only that, we are providing the properly designed baffles. So it is also increasing the turbulence and accordingly the heat transfer coefficient, ultimately overall heat transfer coefficient, and ultimately the heat transfer, total heat duty of the exchanger that increases. Now comes tube layout. What happens when it is a multiple tube variety like shell and tube heat exchanger where the number of tubes are too large? We can pack the tube in so many fashion, like it may be a triangular fashion or rectangular fashion. These are the most commonly being used varieties. Rectangular, this is also called as a square pattern, and this is triangular pattern. Within triangular, it may be rotated, non-rotated, those things. Okay. Now, as far as the tube side is concerned, how do you calculate hydraulic diameter? Hydraulic diameter for the tube side, if I substitute in 4A by P, free flow area and P is weighted perimeter. The coincidence, or fortunately you can say, the this comes out to be hydraulic diameter or the normal diameter, nominal diameter. But when it is shell side, the case is not that simple. Shell may be this big. And initially, for the designer, the person may not be knowing how many tubes he need to insert. So when he's not knowing how many tubes are there, how can he calculate the total free flow area and weighted perimeter? I hope you understand the free flow area and weighted perimeter. Say, for example, for the tube flow, the free flow area is the total area through which the flow is taking place, and weighted perimeter is nothing but the perimeter which is getting wet because of the fluid, pi d. Okay. Now for the outside, inside this is fine. For outside, how it is changing the thing means I don't have any definite boundary or how many tubes are there. So what I basically go with is I define the unit cell concept. So this is the unit cell for the square structure, and this is the unit cell for the triangular structure. Now for this square structure, uh, the free flow area is through which now the flow is taking place, and the weighted perimeter is 1/4 of this, 1/4 of this, 1/4 of this, and 1/4 of this. By means of this, if I substitute, I'll get some value of hydraulic diameter. And that's what is the cell hydraulic diameter, equally applicable for the full shell side hydraulic diameter. Okay. Same is true for this case. I can calculate. Now, whatever the kind of tube patterns I am provided, or I am designing, I am planning, I can calculate the corresponding hydraulic diameter, and rest of the calculations will be as usual. I'm not going to the detail of the calculation because I hope you know how to proceed with the heat exchanger calculations. I start with calculating hydraulic diameter the way I have described. Then it is the Reynolds number. I pick up the Prandtl number at the bulk mean temperature. Then I calculate Nusselt number. Then I calculate the heat transfer coefficient. Then it is 1 by UA, that is the overall resistance equated to 1 upon HIAI and so on. Okay. And then ultimately Q is equal to UA LMTD, if it is LMTD approach. Okay. Now, this is the first and the most important aspect which we had started with. This is the case with the tube structures. Now, if it is not the tubular heat exchangers, just think of how the calculation of hydraulic diameter can be done. But if you understand this philosophy, a unit cell philosophy, or the concept of 4A by P, then you can calculate the hydraulic diameter for any random geometry. And once you decide what is the hydraulic diameter, correspondingly you can assess rest of the things. Okay, so this is what has been shown here. Typical maximum exchanger size, this is there. Now, this is one of the tube bundle, but apart from the tube bundle, what additionally I wanted to show, when I'm putting the baffles, what happens, the baffles, apart from increasing the residence time, it also increases the pressure drop. And one, you can say, unfortunate part of the heat exchanger design and its calculation is, I always want higher and higher heat transfer, that is Q, that is also called as heat capacity. And I am always going for better and better this thing. So when I had started with tubular structure, there is certain heat duty. When I increased or shifted to shell and tube version, this increases. Further, when I increase to compact versions, this Q further increases, provided I'm considering the same area of heat transfer. So Q is increasing, but the sad part is when I'm increasing this Q, correspondingly delta P also is increasing. The pressure drop for the fluid. And it happens so that this delta P increases for both sides of the fluid. And for this delta P, I need to install the pump. Capacity of the pump will be increased. And I need to continuously supply electricity so that that operating cost of the exchanger will be high. That becomes high. So if at all I want to reduce this thing by the normal method, what happens? I need to reduce this also, which generally I do not want. So what happens? I have got some in-between solution. So in case of shell and tube heat exchanger, if I can provide the baffles with certain perforations. Now you can see these are the baffles and there are perforations. Instead of the solid baffles, there are perforations through which the fluid can penetrate partially, but at the same time it will be moving in the vertical direction, means crossward direction also. If that is the case, this is another variety that is called as a rod baffles kind of heat exchanger. This is nothing but an improved version of the shell and tube varieties. Okay. Now, whatever the left-hand side of the thing I am showing, this is not the heat exchanger, but this is basically the tube bundle. All the tubes fixed with the end plate along with the baffles, rod baffle kind of things, and the whole tube bundle now is ready for inserting inside the shell. And the tubes are not put individually. This is put inside the shell as a group, and that's why it is called as tube bundle. Now, when we have done this thing, now you can think of just how the calculation of those heat transfer pressure drops can be done. Okay, I am not going to that detail for this specific case because we need to do so many other varieties also. Okay. Now, for doing all these things, what happens? We generally refer some of the things. There is one agency. This is TEMA called as. This is nothing but Tubular Exchanger Manufacturers Association. This is an agency in US which takes care of design and construction aspects of tubular heat exchangers. Okay, so only tube in tube, shell and tube varieties, whatever different varieties are, it takes care of, and it is doing the standardization. Whatever is standardization like BS code and those things are there, TEMA does for tubular heat exchangers. And how it is doing, based on the design aspects, we are having the nomenclature, front end, rear end, what is shell. Accordingly, now you can see, suppose this is the case. We are having so many varieties, means for the same shell structure, how different categories of the end plates are there, A, B, C, D, and so on. Similarly, right end, rear end, we are having LM and PS and so on. Shell varieties also, E, F, G, H, all these things are there. Now you can see it is entering from this side, going out from this side, or maybe entering here, getting splitted, divided here by means of baffle, then coming out, splitted here, so get divided in two parts and coming out here at the bottom, splitted in two parts here, are divided flow like this, or there are other varieties. So accordingly, if I'm fixing this as front end, this as shell type, this as rear end, means my shell and tube nomenclature will be A, F, and M. That is TEMA notation. Then accordingly, rest of the inner calculations I will start with. This is now the tube bundle at the bottom, not rod baffle. This is the normal shell and tube bundle. And this is what is the photograph of one, you can say, installation, shell and tube variety. Now you can see how big the entry of the fluid and exit of the fluids are, and the total size of the exchanger and the length. Now what happens? What are the problems in conventional shell and tube heat exchangers? Some of the problems, of course, when I see the problem, all the time we talk about the modifications, and whatever modifications we have got, that is also for some or the other reason to overcome those challenges only. So I'll not be categorizing here. These are the challenges and these are some solutions. All the time I'll be talking about some problem and then some solutions. Okay. So in case of conventional shell and tube heat exchangers, what happens? We face different problems. Problems like there is poor shell side pressure drop. Is it a problem? Poor shell side pressure drop means if pressure drop is small, one issue may be you require minimum power, so that may be good in one sense. But at the same time, if pressure drop is small, what happens? The flushing of those sediments, the particles may becomes difficult. So at the same time, the proper flow rate is to be maintained so that there is some significant amount of pressure drop also. You cannot avoid zero pressure drop means it becomes stagnant. So even at different corners also you need to have the circulation of the fluid and corresponding pressure drop at each and every point so that all the fluids will continuously be flowing, giving you the effective heat transfer from different corners, different surface area, and ultimately the flushing of the particles also. So when we are providing the zigzag path that helps us in reducing the pressure drop. That is one thing. At the same time, the problem associated with the zigzag path, cross flow, putting the baffles is the fluid is crossing perpendicular to the length of the exchanger. That leads to the vibration of the tubes. So when it is vibration, what happens? The joints at the end, which in general is a welded joint, that becomes weaker, and after some time, we find that the whole thing will become loose, and finally, uh, there may be failure or the breakage. There are dead spots at certain corners. So whenever there is dead spot means less heat transfer. There maybe recirculation zone whenever there are dead spots, possibility of recirculation zones, those eddy currents will be there. Again, it will be extracting some extra amount of power, and you'll have to pay for that extra power. Fouling. Fouling is another major issue. Of course, when there is fouling depends upon the type of the fluid we are using. But what happens, whatever good quality fluid we use, the filtered quality, those things, with time, there will definitely be deposits. How to overcome that thing? One issue is there must be some sufficient velocity. That velocity, the order of velocity is if it can be 1 meter per second, definitely it avoids majority of the problems of the fouling. But so many times it may not be possible, then definitely we need to take care of the other provisions. Okay. We must avoid the stagnant regions, the spots where there is no fluid circulation. We also need to avoid the hot spots. We also need to avoid the cold spots. Two cold spots also should be avoided so that again there are similar issues as such what we are getting in case of hot spots.
Sir, sorry to interrupt.
Yeah, please.
Sir, as you said that in previous case that baffles in case of shell and tube heat exchangers causes turbulence,
Yes,
and once the turbulence is caused, it causes eddy currents will be generated there,
yes,
right, sir? And which will cause increase in kinetic energy.
yes,
And when kinetic energy of the molecules increases, which it directly increases the temperature,
yes.
can we say it is a negative effect of
See, dissipation of energy is fine, but what happens uh, when it is turbulence along the length and along the flow, that is fine. But what happens, suppose flow is taking place, it is taking turn like this. This dead spot, this dead spot is basically creating not that equivalent effect. It may dissipate up to some extent, but definitely the overall output is not as significant, as effective as what is getting created in case of turbulence in the normal flow.
Yes, sir. Also,
Okay.
there will be, sir, balancing will be the problem because due to turbulence, there will be something, some turbulence movement will occur there. So balancing will be
Definitely. Means
required there.
whenever there is any eddy current, the air pockets, that will definitely create a certain, you can say, pressure differential, and that will further affect so many other things. And definitely, this vibration is also associated with that phenomenon. Apart from fluid moving across the tube, that air pocket, difference of the pressure, all those things will lead to vibration in the overall shell also. Okay. So the vibrations somehow we need to avoid, because whatever good manufacturing technology material you select, once it continuously is facing vibration, after some time what happens, the joints will get broken and there will be leakage issues. So your heat exchanger will not at all be effective. You need to open it, you need to again weld it or remanufacture it till it is perfectly seal proof. Is it okay?
Thank you, sir. Thank you.
Uh, Apart from the normal vibration issues, it leads to sometimes resonance also. Okay, the amount of frequency may be such that it may
Yes, sir.
coincide with the natural frequency of the body or the tube, and there may be resonance. If it leads to resonance, it is further a dangerous issue as far as the operation is concerned. Means failure will occur very soon. For avoiding vibration, definitely baffle is one of the most, you can say, simplest solution we are having. Apart from turbulence, apart from increasing residence time, apart from increasing the total length of travel, it provides one of the best way of supporting the tubes inside the shell. And at the same time, it dampens the vibration also. If we select the proper baffle material, the dampening of the vibration also takes place. So the easiest solution is putting the baffle, which otherwise also is required. But apart from the baffling, there are other provisions also by which we can reduce the vibration up to some or the other extent. Okay. So some of the other things have been shown here. I am not discussing again. There are some more provisions. So apart from the baffles, there are some additional baffles of these varieties come into picture. We call it as inlet support. In between, we put certain, you can say, fixture kind of things. Okay. So that also gives some restriction as far as the vibration is concerned. There are issues with the shell side flow. What happens when the fluid flow takes place only in the shell side? There are certain other problems. Vibrations are there, the supporting of the tubes may be the issue, the deposits, the air pockets may be the thing. But at the same time, we need to check. All the things cannot be eliminated or checked up to 100%, but we need to see how periodically this can be taken care of. So naturally, each and every heat exchanger has got certain preventive maintenance schedule. So if it is meeting with that time schedule, say 6 months or 1 year or whatever, then it is fine. But if it is occurring frequently, it is leading to some other problem, definitely we should take care of that particular problem. Now, when we are solving the problems, the calculations, one way is as what we are doing, that calculating heat transfer coefficient, all these things. But calculation of heat transfer coefficient sometimes is not that effective and not permanent solution. So what happens, we are having another effective substitute for that. Instead of H, we plot this J. This J is called as Coleman factor. I hope some of you might have heard about this thing. And this is something like replacing the heat transfer coefficient, which is having dimension with a dimensionless number Coleman factor. So when I am replacing this H by a dimensionless factor, naturally, now the comparison of different heat exchangers can be very easy. I can compare one big heat exchanger with the smaller one, how effective one is with respect to the other. It is as similar as we are having the specific speed and a specific, you can say, power of the turbine or the pumps and those things. Okay, or any other dimensionless number. Why at all we need dimensionless number? That's why we are having one. But this is very standard practice that the professionals who are in the shell and tube heat exchanger, you can say, field, or any other heat exchanger field, instead of heat transfer coefficient, they generally talk with the Coleman factor. Okay. Now comes the fend variety, but shall we go for the break, Prasarna?
You can go if you wish, sir. So we
So,
can have online coffee and tea.
okay, okay,
Online coffee with me, huh?
okay, okay. So some, you can say, sandwich also.
Sandwiches, huh? Online sandwiches also
Okay,
we can have.
okay. Thank you. So maybe a break of 5 to 7
But,
minutes.
but sir, don't get disconnected. Just switch off your video and mute your voice.
Sure, 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 sure.
Okay, sir. Okay.
Okay, okay. Thank you, thank you. So maybe a break of 5 to 7 minutes.
Yes,
I'll
sir.
come back. Okay.
Sir.
Thank you, sir.
Dear participants, please don't leave. Huh? You can have a break for 10 minutes, 5 to 10 minutes. After the break, you can again join. But don't leave the meet.
Okay, sir.
Okay. Acha, all participants are requested to ask the questions in the end. Danish, it was wonderful you asked a question, but good practice would be to ask in the end. Huh? So your question was very good. Huh?
Sir, I thought कि फिर लास्ट में अगर मैं लास्ट में पूछूं तो
Oh, fine. No issues, man. So it was
Thank
very good question. I liked your question. So in the end, you can also ask. Huh? So go
you,
ahead. Huh? Wonderful.
okay, sir. Thank you.
Bhavani must seem pagal. Dear participants, don't leave the meet. We are starting after 5 minutes again. So please don't leave.
Okay, sir. Okay.
So welcome, sir, back.
Thank you. Thank you. So before I proceed,
Uh-huh.
just I wanted to know your feedback or suggestions, the way we are going, because probably it's taking too much of the time. So I may be doing a slightly fast in some of
You
the
can, you
design.
can, you can, sir, skip some slides also if you want,
Okay,
sir.
okay, okay. Any other suggestion from your side?
But it's wonderful. But it's very informative. It's very basic, na? And very quite this thing
Okay,
exhaustive.
okay.
So now you are coming to the real things,
No,
na?
if you may be thinking that some of the aspects of
No,
people,
no, no, no.
100% of people may
It's
be
really
knowing.
enjoyable.
Huh?
It's really enjoyable. It's very good exposure for the students. In fact,
Okay,
the students can view this thing, view your presentation always on the YouTube channel now.
okay, okay,
Recorded. It's getting recorded there also.
okay, okay,
So
fine.
they'll really enjoy this thing. So this is very good. So you're going really good.
Okay. Let's see how effective it will be for them because I'm talking too much of the effectiveness. So,
Actually, this is really because you have to just talk about the performance of the heat exchangers. Okay, it's fine.
yeah,
And you are just talking about how we can just improve the performance of your heat
yeah,
exchangers,
yeah.
and you are talking about the various problems which you are facing in the heat exchangers.
So, if people have come back, shall I start?
So you can start, you can go ahead.
So, my slide is visible, I hope.
It's visible, everything is okay.
Okay,
Pin tube heat exchanger is visible.
okay. So, welcome back again. The content we were discussing. And this is the next version compared to the previous, the tubular structures. As I told once that human beings are too greedy, so they want always more and more. So this is the next version in continuation to that, which is requiring higher heat transfer area for the same dimensions. How this can be done means that is by putting the extra surface by means of the fins. So fin heat exchangers we had heard so many times. We had seen also in some of the cases. The commonest examples are the backside of the air conditioners, where we are seeing the condensers having tubular structure with certain plate fin varieties, wavy plate fin varieties, condensers of the thermal power plants, the radiators, and so many other things. In and around us, there are so many varieties of the heat exchangers. And wherever the size becomes compact, in most of the cases, it automatically leads to the fin versions. How the fins are being put. So, as I told, it depends upon the heat transfer coefficient. And when it is heat transfer coefficient, it may be either outside or inside also. So now you can have the cross section of different uh, fin tubes. In so many cases, it is outside. These are longitudinal fins along the length. And it may be continuous, it may be, you can say, star form. It may be, you can say, the transverse fin also, like what this one is. Okay, and this is the kind of version we are having in the condensers of those air conditioners generally. So it's not limited to this kind of variety only. We are having infinite version of the fin structure depending upon the size limitation, depending upon the effectiveness, and so on. But here, the one peculiar thing you are seeing that there is one common plate attached to the tubes. So it is the plate which is called as fin, but there is one single plate attached to all the tubes. Means instead of this independent fin for one tube, all the fins have been joined just to save the problem of manufacturing. Means individually fixing the fins, we just put one complete plate, fix it with all the tubes, and that acts as common fin. So that is what is the provision we take just to avoid the problems of manufacturing. Second thing, when the tube structure is too small, like this one, just for one example I'm considering, when tube is too small and over that we need to prepare the fence, the commonest solutions may be either we need to weld it over the tube surface, or we can machine it. Machining that thing is of course difficult. Putting individual pen, maybe shrink fit, compact fit kind of thing. But if you remember the workshop practice, means how the screw threads are being made, the same way even this uh, finning also can be performed. So by means of the screw thread technology over the lathe machines also we can prepare the fins. Again, subjected to whatever limitations, sizes, the effectiveness issues are. Next category comes, that is the compact version. Why compact version? We had defined this 400 or the 700 meter square per meter cube, depending upon whether it is the liquid or the uh, air or the gaseous fluid. With gaseous fluid, it is the 700 meter square per meter cube. Now, if I show you some of the compact versions, even these tube and fin structures, like what we had discussed, fin structures, all these also come within the compact heat exchanger versions. So whenever I'm using tubes, whether here, here, or here, these are called as tube and fin, or tube and plate fin, because fins are of the plate nature. Okay. But if it is plate, like this, and in between there is fin, means there is plate, and then I am putting fin like this, it becomes plate fin. This is plate fin heat exchanger. Okay. Now, how do we manufacture that thing? Let's see that. There is one plate, there is another plate, top and bottom. In between, instead of putting the fins like this, I take one sheet make a corrugated one like this and put it in between the plates, compact it. From the side, I put the side bars and then join all these things together by means of either diffusion bonding, okay, or brazing. Generally, these heat exchangers are made of either aluminum or sometimes stainless steel also. So it may be either diffusion bonding or the brazing process by which we prepare the heat exchanger passage. This is one passage, but likewise, only one or two passage may not be sufficient because the amount of flow rate, amount of heat transfer requirement be significant. Second thing, what do you think? What may be the size, dimension of this, height of this? This is simply of the order of say 10 to 15 mm maximum, starting from 5 mm even. 5 mm small things are also available. So 5 to 10 mm height means the passage is not that big. And that's why for each fluid, I'm having the alternate passage. Like this is suppose cold fluid, this is another cold fluid, this is another cold fluid. Same fluid is getting divided in three parts. From the other side, I am having hot fluid. And now they are making a sandwich kind of a structure, like what the break you are having. This is not e-sandwich, of course. So this is the compact heat exchanger. Now the issue is, I'm having one pipe or the tube bringing the fluid. How to connect this tube to this? That is basically a major issue here. Apart from construction of the heat exchanger, the connection of the exchanger with the main fluid line also is a major challenge. How to take care of that thing, we'll see in the coming slides. Now, the type of fins, as I told, there may be corrugation sheets, but corrugations can also be of different varieties. It may be corrugations in rectangular nature or triangular nature. Further, as I told, human beings are greedy. So they are not satisfied with this much enhancement of the heat transfer area also. So they put further perforations so as to enhance the heat transfer coefficient, turbulence, make it waviness, further lowering of the surfaces are there, or it may be offset strip fin. Means the same rectangular fin, I cut it from here and then offset it by 50%. So what is happening? The flow passages become like this. Flow enters like this, get divided here. Further, it gets divided here and so on. So what is happening? If at all, the boundary layer is starting here, this cutting up boundary layer, fresh start up the boundary layer from both the side and so on. So starting and cutting up the boundary layer frequently will lead to enormous enhancement in heat transfer coefficient. Okay, so that is the biggest advantage, that in spite of being the smaller version, very compact sizes, the limitation of the sizes because of the compactness, at the same time, because of the limitation of the technology we are using, the vacuum brazing furnace, whatever we use, the maximum size we can accommodate is hardly 30-40 centimeter or so, keeping other allowances into account. Okay, so beyond that, we do not have. So 30-40 centimeter means less than half a meter. That is the maximum size. So if at all we are having that is the maximum size, definitely we are going for much higher heat transfer coefficient, and we are achieving also by these provisions. Okay, so surface area density is too high, weight and size is very small. That's why they are compact one. Heat transfer coefficient too high, but this is the low friction and pressure drop. What I am saying, this is definitely lower, but compared to the other version of the heat exchanger, this is still higher, much higher. Okay, I am saying low because if you compare this with the enhancement of heat transfer, the corresponding increase in pressure drop is not that high. But if you compare this pressure drop with the shell and tube or tubular variety, this is enormous. But then who will go for this high pressure drop kind of thing? The reason is these are the exchangers very commonly being used in aerospace, cryogenic rockets, aerospace applications. Like you must be enjoying the flight with cooling provisions at whatever the height or outside conditions. Okay, so for that there are number of fluids, refrigerants inside going through, and inside you will find that there are so many compact heat exchangers working with in the cabin. Okay, there we are having those compact passages with two, three or multi-fluid cases, and there we are having such kind of plate fin heat exchangers. Now, as what I told, there is enormous heat transfer. That's what we want. But at the same time, there is very high pressure drop also. But then the kind of application we are happening using, it is the aircraft. So basically, the requirement is the high heat transfer effectiveness, the low cost, the low volume, size, and weight. That matters more than the pressure drop. So even if the pressure drop is high, we are providing high power for that. Uh, we are ready to pay because we are getting some, you can say, advantage against that. And that's the reason wherever we are having such kind of, you can say, applications, whether the aerospace or defense things, we do not bother about the cost. It is basically the size and performance which matters the most. And there basically these compact flint passages are being used widely. Now, there comes the flow arrangements. Now, if you see the flow arrangement, you will find that the fluid is entering as what I was telling, it is coming out. This is cross flow variety. Now, what happens when it is entering? There is sudden contraction expansion effect you might have heard of. Okay. So there is sudden expansions and sudden contraction here. These are not the desirable effects in terms of the pressure drop, the eddy formations, the blind spots and those things. So what happens, suppose I consider this as one passage. I cut the fin like this. I cut the fin like this. Okay. In between, I am having, sorry. These are the fins. But in rest of the portion, I simply put the vertical fins. Now the fluid enters from here, move perpendicularly, and then come out from here, perpendicular direction. Now the total passage through which is entering is small. The total passage through which it is entering is small here. And it can well be connected with a tube here. Same is true for the next layer. So now the handling of the fluid is easier. And that is what is happening. And this provision along with this attachment is called the header attachment. So there are varieties of the headers. Some of them may be clear here, but in general, this is the varieties we are handling with. And the header design also is a very important aspect as far as these compact heat exchanger construction and manufacturing are concerned. As I told, there are Coleman J factor and then F. And people have done so many experimentation. Now there is one question: why at all such correlations are available? People have done so many things. Now these are basically the characteristics. Whatever these J and F we are calling it, these are the heat transfer or the pressure drop characteristics. What do you mean by characteristic? That identifies. It is the identification of that heat exchanger. So whenever I am doing the testing, I'll try to take up that aspect at the last portion. In this testing of the heat exchanger or experimental performance estimation, I basically try to calculate these two aspects, J and F. Now, when I'm doing this thing, do you think that JNF is the characteristic of the heat exchanger? I hope everybody must be thinking that way only. But then one peculiar thing I'll tell you, that this JNF is not the characteristic of the heat exchanger. This is the characteristic of these surfaces. So for the same heat exchanger, if I change the surface, JNF characteristic changes. And that's the reason when I'm going for the testing of the heat exchangers, it it is the calculation of JNF, but calculation of JNF for not for that compact heat exchanger, not for that shell and tube heat exchanger, but basically for the surface characteristic. So if I have selected this particular fin, say for example, this particular fin with certain dimensions, means the characteristic gets fixed. Now, whatever size of the dimension of heat exchanger I take, smaller or bigger, the JNF characteristic that remains the same. Means if somebody has tested that particular size, means it is once for all. It can well be used by you, me, and anybody else. Okay, and that's the reason these people have done so many experimentation and generated something. But then we also invent so many things. So I change some of the dimension, it becomes new fin. So initially, some of these people like this case, and there is one more person you might have heard of, one London. These people have done so many experimentation. This is the group for US Navy in 1950s and 60s. They generated so many of data and published some data book kind of thing also. But then afterwards, people think that we are doing this testing, and I'll show you some of the diagram. This testing is not that easy. Not only in calculation respect, the effort wise, time, money, and the experimentation part, it is very rigorous. So when they are doing this effort, people thought that why to make it open? They stopped making it open, and then afterwards, uh, once you are ready to pay this pay for these characteristics, then only it is made available. Okay, so it is something like people do all these experimentations, and then they say that these data are available. Like now, everything is available in market, our personal data also. So it is also something like that. You pay for those data and get those characteristics. If at all those standard fins are available. And that's the reason we now select the standard fins from the list of standard dimensions available. We use them without testing it, and those testing data, we pay for them and get those testing data. And that's what the commercial people are doing. So whosoever they are in the industries or R&D of these heat exchangers, they are doing that way. So likewise, there is so many. These correlations, of course, are open, but if you want data, that is a tricky thing. Another issue, as I told, that the transition, where transition is taking place. As I told, when I'm reducing the hydraulic diameter, the transition at which the laminar to turbulent transition is taking place, that changes. It goes down. Means instead of 2300, the transition takes place at 23 and 1500, maybe 1000, or sometimes less than 1000 also. So how to get that idea? People have suggested something, that they have given some RE star calculation of RE star, how that is there. Each person has defined something. Even calculation of hydraulic diameter also, people have done different ways how to calculate the hydraulic diameter. It's not that simple. I told, if we go to finer details, even calculation of hydraulic diameter, that itself becomes topic of research. So that way, some of these data just for the preliminary calculations research is available. But if at all somebody wants to go deeper, definitely a lot of efforts and experimentation is required. Otherwise, you need to pay for these things. These are some more data and calculations for that, how to calculate hydraulic diameter. More details are available. I am not going to much detail for this. Pressure drop. Like heat transfer, we are calculating the pressure drop, where from actually the this friction coefficient F that comes. That also is a tricky issue. Suppose this is the heat exchanger core. Not only the pressure drop takes place here, but the pressure drop takes place at the header, entry header, as well as at the exit header also, where the sudden contraction and sudden expansion is taking place. So if I sum up all these things, you will find that there are so many components. Means between 1 to 2 pressure drop like this, 3 to 4 pressure drop like this, and between 2 to 3 the normal pressure drop. That normal pressure drop is again not that simple. It is 4 FLG square 2 rho DH, something like that. Provided I have got some constant value of density, all these things. While the gaseous flow is flowing through these compact passages, the effect of those compressibility also come into picture. And if at all that thing is changing, we'll have to incorporate that aspect also. Okay. So the calculation of this heat exchanger pressure drop, again, if you go to precision level, it contains three components, major components, and summing up all those things will lead to the exact value of the pressure drop. Therefrom, equating that to here will lead to the value of F along with J, that gives the total characteristic. Okay, so this is entrance, exit, core friction plus momentum, that compressibility effect I was telling. Okay. Now, how J is defined, that I have not told probably. J is, there is some relation with the H, heat transfer coefficient. This is Stanton number into Prandtl number to the power 2 by 3. And this Stanton number is H upon GCP. So if you know heat transfer coefficient, this J can be calculated. So basically it is non-dimensionalizing the heat transfer coefficient with respect to the fluid you are using, PR, and the mass flux velocity and the properties. There is plate variety, which is being used in the milk chilling. And the speciality of this is, again, here there are plates available, but instead of the fins, sorry, there are corrugations like this. The plates are made with the corrugations, and then the plates are compacted with each other. There is gasketing, and then the provision of the hole is such that, suppose this is one side of the plate, fluid will be entering here, going out from this. Side, fluid will be entering from this hole, going out from here. And there are alternate passages. So one passage, cold fluid will be there, another passage, hot fluid will be there, cold, hot, and so on. Another great advantage of this, that this is something like we can put so many things in series, put one solid bar, and then through the nut bolt arrangement, we can prepare the heat exchanger. So heat exchanger is something like assembly of the plates. And disassembly also is very easy. Cleaning is also very easy. So that way it is very flexible one. If at all you want to increase the heat transfer capacity, put 10, 15 more plates, and that becomes a bigger heat exchanger. So instead of going for a newer design, newer size and those things, just it is simply addition or removal of some of the plates so as to meet the capacity of the heat exchanger. Okay. Cleaning is easy, maintenance is easy, all these things. And that's the reason for milk chilling, this is the best suited one. Advantages, we are having so many advantages like plate heat exchanger. This is the compact version, but at the same time it has got so many you can say advantages of the other things. Turbulence is high, no stagnant uniform fluid flow, no contamination, no fouling, all these things. But at the same time, the issue is it cannot be recommended for gas to gas applications because the passages available are too small. So it cannot accommodate the high volume, high specific volume. Similarly, for very high viscosity fluid, this cannot be recommended. Wherever flow velocity is less than 0.1 meter per second, again, this is not suitable. And like gases, even for the steam also, it is not suitable. Some other variety of the plate heat exchanger is not plate fan. The previous version I told, that is the plate heat exchanger. Instead of putting them together, then bolting all these things, we can weld them permanently like this, the corrugation one, and that makes the passage permanent. This is a permanent one, so this is called as welded plate heat exchanger. Okay. This is die-stamped plate coil heat exchanger. Now, probably if you happen to see the just slightly older version of the refrigerators, there the evaporating coil are the freezer compartment. There you might have seen this variety, freezer. So it is nothing but the two plates of aluminium brought together, and in between we are having the die stamped fluid passage through which the refrigerant is flowing. Okay, so this is also one very common variety of this thing, but application is limited. Not every place we are using. The commonest application is the freezer, the older version. Nowadays we are having some other category of this heat exchanger. Printed circuit board. Now you see the dimensions. This is hand, and this is the size of the heat exchanger. These are further tiny passages. But then if we go to the application, these are being used for very bigger size, bigger version of the heat exchangers, especially in nuclear reactors even. Okay, now if I further show you the size of those printed circuit board heat exchangers. Printed circuit board doesn't mean that they are being used for those laptop PCBs and those things. They are much bigger versions, generally for those, as I told, the nuclear reactors. And now you see the dimension. It is as good as shell and tube heat exchanger dimension, bigger things. But at the same time, if you see the capacity, how much heat transfer area or the surface area density or the heat capacity it may be handling, now you just compare. This is the shell and tube heat exchanger, and correspondingly for same application, if I am designing the PCB heat exchanger, this will be the smaller version I am having. Okay. So this much reduction in the dimension or the size is there, and that's the reason the nuclear reactors are using these kind of things. We are having regenerative heat exchangers also, which is working on the function of this regenerative concept. Basically, they are either fixed type or rotary type. Application point is, if you happen to visit the thermal power plants, almost 70 to 80% of those air preheaters are of these varieties. The easiest thing is how to manufacture this thing. We are putting this thing only the side walls, and inside we put the wire mesh. That works. But how the handling of the fluid is, we basically divide the total fluid compartment in two parts. One side, hot fluid will continuously be flowing. Another side, cold fluid will continuously be flowing. In between, this is rotating. And the rotational speed is of the order of 3 to 4 RPM. Very small because the residence time has to be sufficient enough. If we increase the speed, the heat transfer may not be possible. But the disadvantage is whenever this side moves to this side, having interaction with the other fluid, the dilution or the mixing of the fluids takes place. So this is only applicable or limited to those conditions where the dilution of the fluid has not great effect on the performance. like in the air preheater, if at all the fresh air going inside gets diluted by the hot gas, hot flue gases, probably there may be more amount of fresh air needed, but it's not affecting other components. Similarly, the flue gases which is going out gets mixed with the fresh air. Probably we are losing some amount of fresh air, but that's not affecting any other component of the thermal power plant. Okay, so this is what is the regenerative concept. I'm skipping this design theory. Now, when we are designing, at the same time, I told that we need to optimize also. And when we are optimizing, uh, the general philosophy is how to optimize those heat exchangers. Because generally optimizing either Q, maximizing Q, or minimizing delta P, these are the common things. But at the same time, uh, this may lead to further some other things like so many times, rather majority of the cases ultimately converge to economics only. So all the time, if you ask somebody whether which kind of category, which particular type one is willing to buy, he see his or her pocket only, and based on that, the decision is taken. Like you're going for purchasing a mobile, so you try to optimize that with the same 15 20,000 or 40,000, what best category of the mobile phones you'll be having. So ultimately it is the economics which plays a vital role in decision making, and ultimately the optimization of the design. So when it is heat exchanger design, say for example, if I'm optimizing the cost, minimizing the cost, that minimizing the cost is cost of the heat exchanger. There are minimum two pumps running, so the initial cost of that thing plus the operating cost of the two pumps. If at all it is an old, you can say installation, there will be maintenance cost also, periodic and the other maintenance things. So if I go on calculating these costs in terms of these values, and further this is area of heat transfer, pressure drop. These need to be substituted in terms of the parameters of the exchanger. What happens? There may be 10, 15 or 20 number of these parameters. So if we go for those 20 number of parameters, uh, what happens? Uh, we may not be able to solve it using the conventional method of the optimization. Okay, so definitely we need to look for certain alternatives, and for majority of those heat exchanger optimization, we need to converge to some non-conventional techniques, which is, I don't know how many of you have heard of these things. These are very non-conventional one, but at the same time, they are based on some or the other philosophy of our life, or some simulation of the metals, this annealing of the metals and so on. Bees colony, the ant colony, the movement of the elephants in the hills. All these are considered as the concept for algorithm, and those give us the algorithm, and based on that we try to make these things. Of course, these optimization techniques do have certain issues also regarding the convergence, regarding the global optimum solution and those things, but still they are worth using because the other optimization techniques generally fail for such kind of applications. So I am skipping again some specific cases about these, which I wanted to discuss, of course. Then coming to the testing part. I'll take 5 more minutes, then probably we can have some discussion, short discussion. When I'm trying to go for the testing, are the calculations even. You might have seen that we have so many assumptions. We neglect heat losses, we neglect the turbulence in the flow, we assume a steady condition, no energy generation, internal heat generation, and so on. So whether we are simulating it or doing the experimental testing, it requires the incorporation of those aspects until those are not the major things. So this is one heat exchanger for testing is being manufactured. Compact heat exchanger, of course. How the internal construction is, that has been shown. Now, if at all I ask you to calculate the performance, the simplest performance calculations, we know that this is Q is equal to MCP delta T. Okay. Now, when it is MCP delta T, where from all these values are coming, where the heat exchanger geometry is coming. So, if at all we go to those finer details, incorporating the actual conditions, it is something like that. It may be Q is equal to HA delta T, then from one side to the other, it is doing like this. For one fluid, another fluid, in between, from one fluid to the other fluid, again crossing the boundary. Now, if I consider the temperature variation along the length, I definitely need to uh, model it using certain differential equation, partial differential equation. If I consider the conduction taking place in the solid wall, I need to further incorporate some more term. If I consider the conduction in the fluid, which is generally considered as axial dispersion in the fluid, I am involving some more term like this. So now, if it is a steady condition, it is fine. But if it is transient condition, the accumulation of energy, those things also I need to. So the total number of equations for this two fluid heat exchanger would be something like this, having all these temperature and the uh, other variables. Now, if you need to solve, definitely you need to solve these three partial differential equations, and then you can calculate the exit temperatures. Based on that, you can calculate further, go back to the other calculations. Okay, but this requires again a trick. Not analytically you can solve this complex setup equation. So numerically you'll have to go for and can calculate. Definitely it's a solvable thing, but not that simple as what we do in case of our normal heat exchanger calculations. So if you require that detailed incorporation of those, you can say, cases, definitely need to go on incorporating these parameters, means avoiding the assumptions, incorporating those things, get better and better and accurate solution. There are certain issues like when I'm considering the temperature or the flow taking place, it is not uniform. So these non-uniformities in temperature or the flow, I need to incorporate. Okay. So these are called as non-uniformity or maldistribution. Maldistribution in temperature and flow. Then there are three fluid heat exchanger variety. I am now summing up. I am skipping this portion. Three fluid heat exchanger are furthermore, you can say instead of two fluid now, if you need three fluids, the number of equations, total number of equations you need to solve will become 5. It is furthermore complex situation. So there are cross and the parallel varieties, and manufacturing, designing all these aspects are a bit difficult. There is some suggestion, some solution from our side that how all those variants can be summed up by this variety and can have one single solution. Now testing, finally testing. If I'm saying that I need to calculate JNF, the kind of setup I require is one wind tunnel. Then for one side, I need to provide the condensing steam. So definitely one boiler will be there. Then pressure reduction valve, those things, one condenser portion will be there. Other side, the air is flowing and it will be passing through the thing. Series of calculations by which I am calculating F and G. And the kind of the heat exchanger core, that is something like this. So this is heat exchanger core. This is the total setup for heat exchanger testing. This is steady state one. There is transient testing technique, a bit simpler, but then a much more complex than the steady state calculations. Okay, so we need to decide which one is good for us. For non-uniformities estimation, for not only for the calculations, but for the experimentation also, it requires so many provisions, how to provide non-uniformities estimation, assumptions with respect to the actual ones, how different measurement and all other issues can be handled. So this is one just short glimpse of that. Okay. So I'm skipping this thing, and then finally the conclusion. So heat exchanger, as what generally we know, it's very simple system, but very versatile one. In finite applications, in fact. So the challenges are how to go for effective design, manufacturing, the operations, measurement, and precise control. But then if we are able to manage all these things effectively, the applications and ultimately its performance will definitely be a successful thing. That is a guaranteed thing. And that's what we want. And nowadays, when we want better and better performance, heat exchanger is probably one of the most common appliance for the effective energy utilization, recovery, and better performance. So thank you from my side. If you have got some questions, probably we can have short discussions.
Thank you, Professor Mishra, for a nice and exhaustive lecture on heat exchangers. So now the floor is open for questions. So dear participants,
Good
if you
evening.
have any queries, questions, you can ask. You can raise your hands and one by one you can ask the questions. Miss Hafsa has raised the hand. Please ask the question.
Hello, sir. Actually, my question is about.
Miss Hafsa, please introduce yourself and then ask the question.
Okay, I'm Hafsa Reis, and I'm currently pursuing my BTech in mechanical engineering from University of Kashmir.
Okay, wonderful.
And yes, and basically my question, there are two questions from the baffles. In shell and tube, we used the perforated baffles. I
Yes.
didn't get what was the main motive of using it. That is the first question. And the second question is, if we are using the perforated ones, this means that the holes will increase the stress concentration, and it will make the baffles more prone to the failures. And we know that there is the pressure difference. That how come are we using those perforated and not the normal ones?
Perforations basically reduces the pressure drop. That is one thing. As far as the stress concentration is concerned, the mechanical stress concentration is, instead of the higher one, in my opinion, definitely it will be lower, because the baffles, the obstacle we are putting in the direction of the flow, that is now less, because the whole wall is not obstructed. Partially it is obstructed. At the same time, we are allowing a part of the flow also. So total pressure
Okay.
drop that gets reduced, but definitely we are losing something in terms of the heat transfer performance. It is some kind of compromise in between these two.
Okay, sir. So, and one last question is that since there is some pressure difference, then why are we using that basic equation that Q is equal to mCp delta T? Then how are we using that specific heat at constant pressure when there is still some pressure differences between the shell and tube or any other heat exchanger for that fact of matter?
I couldn't get this question. Can you explain?
Yes, sir. So the basic equation that is Q is equal to mCp delta T.
Yes.
So there the specific heat we are using that for constant pressure.
Yes.
But we saw that there is some pressure differences. When
Yes.
there is some temperature gradient, there might be some pressure differences. Then
Yes.
how are we using that for the constant pressure?
Basically all these calculations, as what I was dealing at last, that was in hurry, of course. All these are with respect to certain assumptions. So whatever these basic equations are, it contains so many assumptions. That's what I wanted to convey. I could not definitely, because I was in hurry at that last moment. It contains so many assumptions. When we want to avoid those assumptions, it becomes more and more complex. So it will no longer be mCp delta T. The things will become much more complex, and as what I was showing, it becomes a very complex equation of that variety. Okay.
Thank you, sir.
Next person.
Now, Miss Atuf, you can ask the question.
Good evening, sir. Sir, I am Atu Sajjad, undergraduate student at NICT Srinagar, Mechanical Department.
Yeah,
First of
please.
all, your presentation was highly informative. Thank you for your time. So, I want to ask you that how can a heat exchanger be used in a geothermal heating and cooling system to transfer the heat between the ground and a building?
Yeah, see, in case of geothermal heat pumps, basically we want to interact with the energy of thing within Earth, below Earth surface. Okay, so what is the kind of energy transfer device we are having? Generally, we are putting the tubes inside, and that tube will be as similar as the tubular heat exchanger version. But if at all we want to increase the effectiveness and the performance of that thing, one way is increase the heat transfer area, so you can uh, put longer and longer tube. And that's why if you happen to see the photograph or the picture of such installations, it will be very big tube, series of tubes, very long tubes. To reduce that tube length, you can have now the options. You can go for either the fin structure or can go for a better variety of the heat exchanger, so that the thing can still be more compact. That is below the earth surface. Outside also, definitely once you are outside, that interaction of the energy from the fluid which is bringing out, you can have another heat exchanger of another variety. So option is open. It totally depends upon what should be the size of the heat exchanger you are expecting, how much you can afford for making it more and more compact. Is
Yes,
it
sir.
clear?
Yes, sir. Thank you.
So next, Mr. Singh, Prabhkaran Singh, you can ask the question.
Good evening, everyone. I am Prabkaran, a senior mechanical undergraduate at NIT Srinagar, and I'm currently working in the heat transfer laboratory. Sir, I was wondering if we consider the radiator of our car as a heat exchanger, so how can we improve the efficiency of this heat exchanger? And specifically for a region like Kashmir, where our temperature ranges from minus 10 degrees, like minimum temperature, it can go to minus 10, and maximum during the day it goes around 15 degrees Celsius. So at a place like this, how will we increase the efficiency?
Efficiency means, are you worried about the freezing of the coolant, or what? If it
Yes, sir.
is,
Like we need to even keep that in mind so that the coolant does not freeze and it is able to dissipate maximum heat even in lower temperatures and temperature above 0 degrees
yeah,
Celsius.
so if it is the freezing issue, definitely see at that small temperature, one thing is that from the engine side, the load will not be that big. That's one thing. Okay, so you don't require that high energy interaction demand. That is for sure, because outside environmental temperature is too low. That is one thing. Second thing, up to some extent, certain additives are there which can take care of about against the freezing thing. Third thing, regarding the efficiency issue, if at all you want to increase the efficiencies, you can change the outside environment. That is by changing the fin passages. You can change the flow of air. Of course, flow that comes from directly the when vehicle is moving, the natural air which impacts on the radiator, that acts as the forced convection fluid. But that can further be improved by providing proper grill, proper fans, all these things. So there are a number of options. Which option is of major concern to you? Accordingly, you can handle that particular thing.
Okay, thank you so much, sir.
So next, Mr. Koshan Kagi, you can ask the question.
Good evening, sir. I am Koshan Kari, senior mechanical student from NIT Srinagar. My question might be a little bit off topic. Actually, my field of interest generally lies in interdisciplinary fields. So I was going through your wonderful profile and I came across this thing, application, your area of interest basically lies in application of soft computing tools. So for someone like me or for someone who is from mechanical background, what sort of prerequisites should he or she have in order to get into application of soft computing tools?
It's not any prerequisite. Basically, like uh, I was talking about the optimization. So that was linked with that soft computing tool thing. Like you can solve those optimization issues, the problems which cannot be handled in general by the other conventional techniques can will be handled by those non-conventional techniques like genetic algorithm or simulated annealing or further some more things. Okay. So as far as that thing, you must know the fundamentals of the basic calculus or those things, and some background about optimization theory. Okay, optimization theory, everybody knows. Probably you are using this basic concept of optimization since your school days by differentiating the function with respect to variable, equating it to zero, without knowing that this is basically the optimization you are doing.
Yes, sir. Yes, sir.
Okay, so
Yes,
with that basic thing, you can go ahead with that one. It doesn't require very specialized requirement.
yes, sir. Got it, sir. Thank you.
Thank you for this thing. So next, Mr. Said Falak, you can ask the question.
Good evening, sir. I'm Saeed Falak, BTech Mechanical third year, NIT Srinagar student. Well, I wanted to know how can a heat exchanger be used to improve the energy efficiency of a refrigerator or air conditioner?
Yeah, in case of say air conditioner, refrigerator, generally what happens, the thing is it has got very low effectiveness kind of thing. Let us consider the air conditioner. If you want to increase the performance of the condenser portion, the backside of the air conditioner, then what happens with time? There are deposits. Uh, the vent passages either get damaged, they get compacted, the flow passage becomes choked, either because of the damage, physical damage, or sometimes because of the dust particles getting deposited on it. So frequently, if you can clean those things, that is removing the dirts, that increases the effectiveness or the efficiency of that system to a large extent. Further, if you are having certain brush kind of thing, removal of those passages, and then having proper environment, that will further lead to some more enhancement of the. But basically, it is the cleaning only. If you can clean the surface, you can clean the, you can increase the performance up to some extent, provided it has got the major issue because of those dirts or the deposits. Any other thing you wanted to ask about this?
No, sir. Thank you.
Chaliye. So next, Ms. Janice, you can ask the question.
Yes, sir. Good evening, sir. I'm Jani Sanif, third year BTech undergrad in Mechanical Engineering Department at NIT Srinagar. You said about baffles, like baffles are used in shell and tube type heat exchangers, and they are basically used to increase the residence time. So I wanted to ask, like, if we increase the time of fluid inside the heat exchanger, fluid will gain the heat and the temperature difference will decrease. And as a result of that, the heat transfer rate will also decrease. Won't that affect the effectiveness of the heat exchanger?
See what happens. We always want the two fluid to become closer and closer. And that minimum temperature difference, I had not touched that aspect, is called as pinch point in case of heat exchangers. So minimum that pinch point temperature difference is, better is the effectiveness of the heat exchanger. Of course, compared to the large temperature difference, the rate, of course, decreases. Rate of heat transfer decreases, but smaller that pinch point temperature differences, your overall effectiveness of the heat exchanger is always better.
Oh, okay, sir. Thank you. Thank you, sir.
So next, Mr. Akash, you can also ask the question.
Department NIT Srinagar. Sir, you have taught different heat transfer technique to improve heat transfer in heat exchanger. Sir, I want to know that what is the scope of increasing heat transfer in a heat exchanger by changing the material like ceramic heat exchangers.
Ceramics also are one of the newer, you can say, materials being used. But basic issue with the ceramics is it has got certain issue with respect to the thermal conductivity aspect. because of the limited thing compared to the metals, it has got certain limitation. Otherwise, for certain specific applications, about the fluid and about the temperature, the specific temperature and surrounding conditions, that is one of the specific, you can say, material being used. We have started using that ceramic also. Means non-metallic heat exchangers.
But sir, some ultra high temperature ceramic, sir,
Pardon?
but sir, ultra high temperature ceramics having good thermal conductivity like zirconium diborides and zirconium diborides. Can we use them as
Can you repeat?
heat exchanger?
Mr. Akash, your audio is not you're not audible. So please repeat the question, or you can type this thing on the. Mr. Akash,
Sir,
you're not audible, huh?
some materials having.
No,
Yes, sir.
your voice
Please,
is
am I
breaking.
audible?
Your voice is breaking.
Okay.
Okay,
So,
you
is I
can
audible or not?
you are audible.
You are audible, but your voice is breaking in between. That's the key.
Okay.
You can write the question.
Sir, so some materials, some ultra high temperature ceramic material like zirconium diborides and HFB2 having good thermal conductivity. I think approx two metals like that can be used as them as heat exchangers.
Exactly, that's what I told. Nowadays, we have started using those ceramic materials. So those are the replacement for that. We are going for better thermal conductivity materials. At the same time, the temperature conditions, the surroundings, suppose we are having some heat exchangers surrounding as the flame and those things, there those heat exchangers are very effective. And at the same time, those can manufacturing technique can also be better compared to the other normal conventional techniques. So those two aspects, keeping that thing in mind, we have already started using that thing.
Okay, thank you so much, sir.
So we still have Mr. Ahmed. You can
Good evening, sir.
question.
My name is Amir. I am a research scholar in Heat Transfer Lab. Sir, I just wanted to know the heat transfer increases by including baffles and other stuff, and as well as the pressure drop is also increasing. Are there any single metrics to quantify the overall impact in increase in heat transfer and pressure drops? And what are the different metrics that we can use to, if there are these single metrics?
See, in general, for any thermo fluid experimentation and the solutions, we have got the ratio, it is thermal performance factor, we call it as. That is the single factor we generally discuss. But for heat exchanger, that is generally not the advised parameter. We separately deal with heat transfer and the pressure drop, but at the same time we try optimizing the best requirement. The optimum solution can be sometimes what happens, as I quoted one example, for aerospace defense applications, there is no harm paying for even extra for the higher pressure drop if we are getting the better and better performance with the small weight, size and volume.
Okay, thank you, sir.
Anyone else? Akash. Okay. Okay, thank you, Professor Mishra, for a highly interactive discussion on heat exchangers. You have answered all the questions posed by our participants.
Thank you. So it was my pleasure if I could satisfy some of their.
You have satisfied all the participants, but unfortunately now we cannot offer you online dinner. So you have to go to your home and make dinner. So next time, maybe you can visit us. I can host you for lunch and dinner, and we can convert this online stuff into offline.
For the time being, I'll be having my dinner with my family, and assuming that you are also the host of that.
Okay. Bye bye. Yeah. So
okay. Bye. Good night. Good night, everyone, and thank you for the patient listeners.
Okay.
Thank you all. Bye.
Okay. Thank you, sir.
Thank you, sir.